Hey guys, how you doing? This is Coach Scott. This is our first video. We're going to be talking about that big ugly word called stoichiometry, but it's really not that bad. Okay, and we're going to talk about it and see what it is. So, stoichiometry comes from two Greek words, stoichion, and that means element, all right, and metron, which means to measure. So what stoichiometry really is? To measure the elements. Not hard. So we use stoichiometry every day. We really do. It's like baking a cake, okay? Or baking cookies. We're measuring the elements used to make the cookies. So we've talked about airbags, right? In cars. They save thousands of lives every year. When a collision happens, wearing your seatbelt, this reaction occurs. 2 moles of sodium nitride, a solid, reacts. I think it's shot off by some electricity or some flame. And it's going to produce 2 moles of sodium plus 3 moles of nitrogen gas. Now, in order for this to properly inflate, you need about 50 liters of nitrogen gas has to be produced. So, engineers determined using stoichiometry, okay, that you need about 96 grams of sodium nitride that you need to put in that steering column to react so each of those airbag capsules will produce enough nitrogen gas. So that's pretty cool, 96 grams. Okay. So let's look at this reaction, right? We've got to have the coefficients in the balanced equation. And we're going to get into balancing again. Hopefully this will be a review from 9th grade or 8th grade science. But we'll be balancing some reactions. But right now I'll give you the balanced reaction. Those coefficients, like the 2, and if there's nothing there, we understand it to be 1, and there's a 2 there. That's what gives us the ratio of moles of the reactants and the products. So I can read this like this. 2 moles of hydrogen gas plus 1 mole of oxygen gas yields 2 moles of H2O, or 2 moles of water. So that means I have a ratio, right? For every 2 moles of hydrogen gas, it's going to react with 1 mole of oxygen gas. And for every 2 moles of hydrogen gas, it's going to produce 2 moles of water. For every 1 mole of oxygen gas, it'll produce 2 moles of water. All we're talking about is ratios. So that's sort of cool. Keep those in mind. So here's a balanced chemical equation. And it's we need this to perform our calculation. So this is nitrogen plus 3 moles of hydrogen is going to yield 2 moles of ammonia. So we can say for every 1 mole of nitrogen, I'm going to have 3 moles of hydrogen. So I can set a ratio up like that, 1 to 3. For every 3 moles of hydrogen, it's going to produce 2 moles of ammonia. So that's 3 to 2 ratio. Then we can say for every 1 mole of nitrogen, it's going to produce 2 moles of ammonia. So that's a 1 to 2 ratio. All right? And we can use these ratios to determine the quantity of any reactant or any product. All right? So for every 1 mole of nitrogen, you're going to need 3 moles of hydrogen to completely react with it. And that's going to produce 2 moles of ammonia. So, by using this interpretation and looking at this as a ratio of proportion, it's a straightforward answer. It's a straightforward way to answer questions about the numbers of moles of reactants and products. So I can use this balanced equation to determine the maximum number of moles of water that can be created from reacting 8 moles of hydrogen gas with oxygen. Let's see. So there's my formula right there. It's balanced. Okay? So I can use this equation. I'm going to set up a ratio of these substances that interest me, right? And the mole amount to be determined should be on top. In this case, it's water. So they ask how much water is going to produce if I have 8 moles of H2. So my given is 8 moles of hydrogen gas. They gave me that. So I look at my balanced equation and I look, okay, I'm going to set up a ratio. So the one on bottom has to be able to cancel out that moles of H2. So I'm going to put the number of moles of hydrogen gas on bottom. They're asking for the moles of water produced. So I'm going to put that on top. So I'm going to do 8 times 2, that's 16 divided by 2. So that tells me how many moles of water I'm going to produce. All right? So that tells me that 8 moles of water is the maximum amount that can be formed if I have 8 moles of hydrogen. Let's look at this example. 2 moles of hydrogen gas reacts with 1 mole of oxygen to produce 2 moles of water. We talked about that. Here's our question. How many moles of oxygen would be needed to react with 12 moles of hydrogen? So now we're looking at 2 of the reactants, and that's okay. We got to make sure we have plenty of oxygen gas to do a reaction. So we're going to use our same formula, okay? The given was 12 moles of hydrogen, correct? 12 moles of hydrogen. So I'm going to set up my ratio. I'm going to put the given term on bottom from the balanced equation. So that's 2 moles of hydrogen. Then I'm going to take from the balanced equation and set my, this is a new term, mole ratio up. So for every 1 mole of oxygen, I'm going to consume 2 moles of hydrogen. All right. Then I just do my math. 12 times 1 divided by 2, and I come up with 6 moles of oxygen. So if I have 12 moles of hydrogen, I want to completely react it, I'll need 6 moles of oxygen. So let's talk about another one. I was given 12 moles of oxygen, of hydrogen rather, and let's see how we did this. So this is just using ratios. So I'm going to need half as much oxygen as hydrogen because it's a 1-to-2 ratio. So if I have 12 moles of hydrogen, I'll need half as much, so I'm just going to need 6 moles of oxygen when I have 12. That's all I'm doing. I'm doing the same thing, right? So here's our ratios for the production. If I have 12 moles of hydrogen, how much water will I produce? Well, for every 1 mole of hydrogen, or every 2 moles of hydrogen, I produce 2 moles of water. So that's a 1-to-1 ratio. So if I have 12 moles of hydrogen gas, I'm only going to produce 12 moles of water. So however you want to look at it, you're fine. So let's look at a real-world application. So this is 2 moles of aluminum. It's going to react with 1 mole of iron oxide, iron 3 oxide, and it's going to produce 2 moles of iron plus aluminum oxide and a whole bunch of energy. This is how we produce thermite. Okay, this is called the thermite reaction. It releases a lot of heat, and they'll actually use this to weld railroad tracks together. So here's the question. How many moles of aluminum would be needed to produce 7.8 moles of aluminum oxide? I'll give you a hint. If I look at my equation, for every 2 moles of aluminum, I'm going to produce 1 mole of aluminum oxide. So that's a 2-to-1 ratio, right? So this is how we did it. They gave me aluminum oxide, so that's going to be on bottom of the ratio. So 7.8, 2 moles of aluminum were consumed. So here we go, 7.8 times 2, that's going to give me 15.6 moles of aluminum. This is the hardest math we're really going to be doing this year. And I think you guys can handle it. Here's another question. What's the largest number of moles that aluminum oxide that can result from reacting 6 moles of oxygen? So they gave us the the moles of oxygen. So I'm going to set this up. Okay. All right. So I've got 6 moles of oxygen. Then I'm going to get my mole ratio, and I'm looking at my balanced equation, and I want to put the moles of oxygen. And I see there's a 3 right there. So I'm going to put that there. 3 moles of O2. And it's asking how many moles of aluminum oxide can I produce. So I'll look up there and look at my coefficient, it's 2. So that's my ratio. 6 moles aluminum oxide. Okay. So now I do my math. 6 times 2 divided by 3, that's 12 divided by 3. That's going to get 4. Or I can do 6 times 2/3, whatever floats your boat. So 12 divided by 3 is going to be 4 moles. We'll see if I'm right. And I am is C. The answer is C. So again, this is going to be some of the hardest math we're going to do. It's not that hard, but you do have to think. My advice to you guys, write your units. Put it on paper before you put it in the calculator. Okay? So this is the beginning of our study of stoichiometry. So hold on to your seats. It'll get better. Our next video is going to be on particles and volumes of stoichiometry. Okay, this is Coach Scott saying have a great day.